record. So. Right. Here we go. All right. Hi. How are you today? Good. How was the weekend? Good. Okay. Was good. That's good. So did you manage to switch your brain on again? Today? Yes. Oh, cool. That's also fine. Okay. So how's it going with the labs?
I think the link of the last task, the one from SDM, it works, but you need a subscription to read the full article.
No. Why?
Yeah, the Medium. Yeah, you have it's behind the paywall.
Shall we? Let's check. Please remind me during the break. I mean, it's a subscription to where?
The Medium.
Yeah, exactly.
You could just do an account and that's.
Are you sure? I
No,
don't
I
have an account.
I did have
Probably have to
I
do
did
it
have
through
an account.
I don't do this.
Yeah,
Yeah.
Yeah.
and you get the.
Normal at work.
Yeah.
Yes. Then what I want to say. So now we're in week 3, right, of the course, and that means that just to again, so no stress, but to give you a sense of an expected pace of working. So now it's time to start working on lab 2. And by the end of the week to finish working on lab 2, and next week lab 3, and so on and so forth. So because so you should spare some time for the very last lab, which is kind of more time consuming. Yes. Yes.
I may make a comment here because like just last week we finished the 2 courses that we had the previous period, and we finished projects for them. So actually, I don't know, maybe some has the similar situation. I didn't have time yet to start lab 1. My plan was to
Last week was the beginning of this teaching period, so you're supposed to.
for some reason, the deadlines were 31st of October and 3rd.
For you, I would complain on the teacher.
We compare to you.
Okay, so it's all my fault now. Okay, okay, but all right. Fine. Again. So as I mentioned, always, I don't like to be stressed myself, and I don't want to be stressed about it. So. And that's why. So I mean, the hard deadline for lab 1 to 3 is end of November, so you still have time. Then talking about this, I got some emails, not many, but still do get some emails. Please use Discord as much as possible, not emails, for communicating your questions to me. And once again, so the course's schedule is stable, the deadlines are stable, and yes, I know that, I mean, this period, I mean, the period, the teaching period contains Christmas, and then the last week of the teaching period, the period is the first week of January. That is unchanged. And it means that you're supposed to also perform until the end of teaching period. But again, I mean, the course is constructed such that it doesn't require a physical presence in any sense. So you can book your tickets whenever you like. So there are no obligatory physical moments, physical meetings here. So all lectures are recorded and published in due time. But the fact that you are moving to some other country doesn't change the deadlines in January, say. I hope that's kind of understandable. Even if you're an Erasmus student, somehow sometimes there is some misunderstandings. of this kind. All right, but saying that, let's maybe. So my ambition today is to finish the topic of the classical machine learning techniques and algorithms, and I want to go through some internals of support vector machines again. Maybe cutting some corners, not going into super tiny details, but some details are, I think, are necessary to understand from the algorithmic point of view in order to understand the limits, the performance limits of one or another technology. But just support vector machines are interesting in many contexts. In the case of machine learning / AI, in what matter learning again, simply because it is kind of mathematically rigorous technique for learning on the one hand. The second thing is that it has connection to kernel machines, which in turn has connection to the dimensionality and feature transformation, which is very important. And again, practically, support vector machines should be, I mean, the part of your kind of toolbox when working with machine learning. Especially, it is very good indicator of linear separability. So if you want to test your data set on linear separability, so you train your linear SVM, you test you test the accuracy on the training set, and so the if the accuracy is well up to 100%, then I mean from this you can conclude linear separability of data set, simply because of the way how it is constructed, and that's what we will discover today. So this is also the first kind of instance of machine learning techniques which are model based. So in lab 1, so we used KNN, which is memory based. Well, no generalization, but still a valid learning approach. So where you keep most of the, or you keep certain portion of your data in memory, and then you basically do the decision, the discriminative decision based on the proximity to certain values. But and for that you need also the measure of proximity that we talked about last time. But the obvious shortcoming is the limitation. So you first of all, it's hard. So your memory is not made of rubber, so it has finite size. So it's hard to accommodate all the. It's inefficient, in other words, from the memory point of view. Complexity with respect to search, that's a bit. By the way, yeah, maybe I can turn this question back to throw this question on you. So memory complexity is a shortcoming, but what about computational complexity of memory-based learning or efficiency? So let's stay on the fuzzy level. Scalable, not scalable.
I mean, it's what is the order n, and as the number of instances you check the test value.
Yeah. Well, modern techniques, again, modern hardware, so is also kind of tailor-made for tasks of machine learning. They are very good at implementing search in constant time. So in-memory computation devices, and even the devices based on spiking neural networks. So there, so due to parallelization, so the search can be the time complexity can be constant, but again by the cost of. This is yet another discussion that we do not touch. But okay, so the main topic today is support vector machines. And as I said, so this is an instance of a model-based learning. So model-based learning, what is it all about? Helping out. So you create a model of your data in one way or another, or the phenomena that you observe, and so you observe it through a set of features. So you have a vector X, which is contains all your instances of variables, and this is the dimensionality of your task. And then so again, so very roughly speaking, so you also have weights, yes, which is again a vector. So the I, the n. And so you basically construct a model, so which is well, in the simplest case, would be a linear model. So linear combination. So Wx, and normally you also have this free term, which is not dependent on data. And then so this model also gives you a score. So and normally score is well, quantification of which category to which category a specific set of samples belong to. Right, but again, so this is general formulation. So let's jump into support vector machines. So with support vector machines, so we have very intuitive geometric explanation, so or a geometric approach to learning or to data, learning on data. So what does it mean? So we have, and again, it's best to be illustrated on a very simple example where you have two features. So let me say F1, feature 2, like pressure, temperature, and also two classes. So later on, very quickly now we will extend or relax this assumption of two features. This is just for visualization, and but at the end, so we also will see how to tackle this assumption of having two classes. So in other words, we are talking about binary classification. So and in the binary classification, so again, so we have a positive class and a negative class. And but now again, so we are now moving closer to mathematics. So this positive and negative. So yeah, I mean, you can really assign. So I mean. So you manifest this terms via encoding of the labels. So and obviously, so again, referring to your previous experience, so there are different ways of encoding the label. So I mean, if you work directly with multi-class model-based approaches like neural networks, so you can use like one-hot encoding, but it's not limited to this, and there are other approaches as well. But again, for the binary case, again, so it's very intuitive, and again, so it leads to better mathematical tractability to assign a positive label, a positive number to positive examples and negative number to negative examples. So, but again, so we are talking about a case where one phenomena should be discriminated from another phenomena somehow. Let's zoom in the middle, so leave some more space here. So what we want, we want to build a model now of this case. So we want to create a model for the positive class and the negative class. And again, so we start with the linear case. So again, so simply because it's mathematically simpler, tractable. So we want to build a model. So basically, we want to build a line, so touching the border of positive examples. So everything beyond this line should contain only positive examples. And in the same veins, we want to draw a line just touching the borders of the of your negative examples. So all negative examples we want to appear on one side of this line. And again, so now still we are in this verbal position. So what we want essentially, we want to draw the, so, as you can imagine, so so this task is not obvious at all. Simply because you, I mean, there are many points so of samples of a given of each class, and so there are also many opportunities to draw this line. Sometimes, I mean, so it is very hard to find the exact parameterization of the line that just touches the border of this part of the data. But again, so to move us closer to the mathematical formulation, so suppose we can do that, but we also want to find such parameterization of these lines as to maximize this distance over here. And maybe now those of you who learned about SVM before, so maybe, I mean, you see a slightly different order of presentation. So because normally you say, I mean, the problem is formulated as to find a model that is kind of best separates two classes. So I started a little bit from inside out. So we really and you know, I personally find it very amusing and not at all obvious. So when you think about your data sets, so cloud points, so you should have this geometrical sense. So and that's why I'm saying, so if you have two cloud points, so you what you essentially want to do, you want to determine its borders. But then, as a result, what you are building, so you are building a model which is on equal distance from the borders of the points of specific class. And again, so maybe now I'm kind of very sloppy with the terminology. I'm talking about points simply because they are points, and I mean plotted as points. But we are talking about vectors. This is important. So sample or data point. I mean that's what it is for me. Point actually is a vector of so I mean they are related terms, but I mean vector is a collection of characteristics describing one data sample. And obviously, I mean, what is missing here is that, I mean, purely graphically. So you should think about really a vector starting from a region. But I mean, it will simply make this illustration too busy. So they are vectors, but they also our data samples that we want to discriminate. Yes, and what we are about to do, we are about to discover this model that is on equal distance. So this small d. So d is the distance from model or from the model to line uh, class. Okay, so now yet another terminological issue here, align. In general case, we talk about hyperplane, right? And the hyperplane, so the shape of the particular hyperplane depends on the dimensionality. So it's basically the shape of dimensionality n-1. So if we have 2D, so I mean the geometrical shape of 1D dimensionality of single dimensionality is a line. If we have 3D, so we talk about a 2D plane and so on and so forth. So line. Hyperplane in general. What we want to do, we want to really to maximize so that in order for our model to be robust, so to say, against data samples that are borderline. So we want to maximize this distance from the model to corresponding hyperplane to the corresponding data cloud. All right. So let me just come to so maybe we can draw a little bit cleaner this figure. Picture 1, 2, and now just a few examples. So these data samples are described through vector features. So basically, the line that we are looking for, which kind of touches the end of the cloud, so make these specific data samples as support samples or support vectors. So there's support for the boundaries, for the models of the boundaries of the classes. Examples on borders. Vectors. So they are support vectors. So we are, so out of all multitude of data samples that we might have, and as you know, in machine learning, we do have the case of big data. So like take MNIST, we have 60,000, and this is a small data set, data set, 60,000 points. So in deep learning, we are talking about millions or billions of data points. So not all of them are actually, yes.
Are the lines always parallel to each other?
Yes, in the linear case, they are. So they are lines. So basically, we are formulating in such a way that they are parallel. Because if they are not, so they intersect at some point. So we really want to separate them. Yes, but so now we need to start formalizing this thing a little bit, and to do that, we remember our definition of a model. So we will have so basically for these data and other data of positive class. So we will have basically so weights multiplied by feature vector plus b. And these are particular particular samples. So for each and every sample, so in this model, so our model should for the positive class be positive, and for the negative class, so if yi equals +1, and for the negative class, so weights multiplied by some xi plus b should be less or equal -1. So if yi equals -1. So equivalently, so what we can rewrite it as following. So this is these are our constraint. So yi multiplied by w x y plus b. Sorry. I multiplied by w x I plus b plus 1. So the same thing, just oops, what? Why? What's happening? Shouldn't happen. So let me try again. Okay, so we are back in business here. By the way, do you see my screen in Zoom? Yeah, so the screen is shared. Yeah, so far so good, right? And as I told you, so we are about to construct a model for these constraints such that this distance to the model and this one so big D, is maximized. So talking about distance, like this thing. And so we want to maximize distance, which is 2 multiplied by D, where D is the distance from model to support line. Plane. So this is what we want. Again, it's easy to see, easy to formulate it for the case of 2D. In a 2D case, so we so this hyperplane is line. So what was the catch? So here's the thing. So we have so now it's our X and Y. So just basic geometry. So if we have a line over here, so you obviously remember. So there are different ways to describe a line. So one of the ways is a parametric line definition. So which is AX plus BY plus C equals 0. You remember that. Again, so if we normally use it in a form alpha X plus B, which is B. So that is equivalent definition. So you can derive one from another. So and then again, so what we are up to again, so that's the beauty of SVM. So if you have a point on this 2D plane, so you want to find D, so you put perpendicular to onto the line, and so then actually when I prepared a long time ago this class, so I really it's kind of amusing to find all the derivations which are long forgotten, but nevertheless, so this D is described by this formula over here. Let me see. So it's a model of AX plus BY plus C divided by A square plus B square square root. So there are different ways on how you can derive that thing. So what do we have here? We have again our model this model here. So just remember this thing. So we have again, so this is our model. And it is we will or we search it in form weighted as a weighted combination, linear combination of features. Well, as a weighted features. No, this is the matrix form, obviously, plus B. So this is the form of the model that we are looking for. And so here we have so positive. Yes. So in our case, so if again, so if you remember, D is AX plus BY plus C divided by square root of A square B square. So if you map it to this form, so this thing over here, so this corresponds to this WX. So this is a free term, B, right? So this is a vector form, vector or matrix notation, or vector or matrix notation. So indeed, so it's a sum of VIXI plus B. And that's why, so I mean that corresponds to this thing over here. And then this A and B coefficients, so they are basically the weights. So if we rewrite it now, so D is equal to WX, again, vector notation, plus B. And divided by square root of sum of VI squared. So that thing over here, so this is the sum of squares of coordinates. So that is nothing more than a norm, L2 norm of these, right? And now, so we are about to figure out this model over here. And to do that, so we need to go maybe a little bit back to this notation. So we want to this is yet another way to describe our model, so which contains both plus 1 and minus 1. So it can be either plus 1 or minus 1. But since we are talking about absolute value, so it is 1. So in our case, then this D becomes 1 over norm of weight vector. So all in all, so in SVM, oops, what YB? Our we want to maximize noise function, which is so this is our function to optimize, which is 2 multiplied by d. So that is what we are up to. So this is d equals 2 multiplied by d, which is now is 2 divided by the norm. And actually, now we do this kind of pretty much standard move. So instead of maximizing something, we minimize the inverse of it. Minimize 1 over f, which is 1 over 2 this thing. So this is our formulation. So that's what we want. Nothing more. So that's I mean, from intuitive geometrical formulation. So we come up with this problem, but again, so nothing. I mean, further on, we can easily, I mean, mathematically, we can, and it's easier to minimize convex functions. So nothing would actually change if you just divide this to a square. So just to make it convex. So make so this will be f star. To make f star convex. So it's 1 over 2. So 2 we don't touch. So that's so square of this thing. So this is now what we want to optimize. So let's maybe take a short break, and I will maybe so I want to rearrange some stuff to cut some corners maybe. In the meantime. So 5 minutes break. Yes.
How much do we have to write on the report? So the report lab. Yeah.
Well, you have the document.
Yes, I mean, when doing Jupyter, you like have it and then like give the title of answering the question.
That's good enough. Good enough. It was overwhelming. Ja, förstås.
You're taking the lab. Is it only the code? You have the working code? Do we need to comment it?
Yeah,
Something else?
comment all intermediate steps.
Okay.
And so, I can announce it now to all, but I mean, since you are asking, it's enough if you have Jupyter Notebook and you comment in line. So, but I mean, comment, I mean,
In a good way.
in a good way, so that, I
Mm.
mean, when reading it, I understand, okay,
Yeah,
you
okay.
know what you're talking about, yes.
Okay. Yes.
Ja, also.
Weil ich begrenzt, was, okay, wir müssen. Okay, und das ist aber okay, schwer.
I read the thing in the book.
Sí, bueno,
Shall we resume maybe? One question, there were two questions about the same regarding lab reports, which I think is important to say aloud, and maybe if you will view this lecture offline, so it's also recorded. Report. It is enough that you comment in line in your Jupyter notebook. So that, I mean, I don't need stories, so you can do pretty, but the thing is that your comments should be sufficient to for me to decide whether you kind of did all the steps and you know what you're talking about. So, and then now I'm thinking, I mean, I think I didn't specify the submission form, didn't I? I will come back about it. So I'm just cannot decide between converting it to PDF so that I just read it or yes, or just not. Yes.
We're doing this in groups, right?
Yes.
So it's okay to
Yeah.
assume to work together and write everything together and send them the same one.
Yes.
or is that-
Yes. Just to be sure, and again. You see, so this is an advanced level course, and by this, I am pretty sure you have your own motivation to for continuing or finishing up the studies. Working in groups so it's mainly for logistical kind of purposes. Still, while working in groups, be sure that you are able to perform all steps individually. So that's important. But then, of course, I mean, I don't have means to control, and moreover, I don't really want to do that.
We all send it.
Yes, but it's important that you, I mean, each and every member of the group uploads the report. And in the report, please state clearly who did the work. I mean, who is in the group. Right. So let's finish up this topic. Because so now I will try to maybe optimize a little bit the presentation. So the thing that you want to optimize, so this is F, so not to maybe, well, I put it as a star. So is 1/2 of a norm of weights squared. Yes. And then so we need a constraint, so it's constraint optimization. So the constraint is in this form. So the constraint is y I wx I plus b equals 1. So here, so this equality means that so we are talking about the samples placed on the line. Oh, again. Okay. So, but our constraint then is can be rewritten as so G. So y I w x I plus b minus 1. So that is our constraint. Equals 0. So that's just a different form of presentation. And now, so yeah, so in a fast forward manner, so we we solve this optimization problem using Lagrangian methods. Or using Lagrangian. So for that, you construct this function, which is L, which is equal to so the thing that you want to optimize minus coefficients and the constraints. Constraints. And to spell it out again, so it's 1/2 v square minus sum alpha I y I, and then here we have x y weights, vector weights. So this is a specific sample, so this is a weight vector, so this is again a label of specific sample, of particular sample, and the coefficients of how valuable is this sample for the classification, basically. And so this is our B. Minus 1. So that's the thing. So like this. And just for you to note again, so this norm square. So remember, so these are the squares. These are the squares of weights, weight vectors, and a square root of it. So if you raise it to square, so this is this thing is basically equivalent to dot product of two weight vectors. So dot product. But now, so there is a kind of next. So now we start solving this optimization problem, and so then we do it by. So this is our optimization function. So we want to use the context. So we want to find, and it's a function of weights. So that's what we want to optimize, and this parameter as well. So that's part of our model. So what we do, so we have two variables here, or two sets of variables with respect to which we want to find the optimal solution, the minimum. To do that, so we take partial derivative with respect to weights and with respect to B, and make them both equal to 0. So dl dv equals 0, and dl for dg also should be equal to 0. So the long story short, so that's not yet, we are not yet there. So these things, both of them, so that's easy to derive analytically. So this is a function. So this is just the square of weights. So sum of squares. And so if you So here you can open the parentheses, and you can imagine what would be the so that this term will be the derivative with respect to b. So b is present only here.
Sorry,
Yes.
when you go away, we are not able to hear you.
Oh yeah. Sorry. I just said that. Taking this derivative of L with respect to V, and B is not a complicated business. I just write the final result. So with respect to weight, it will be so W minus, and then sum of alpha I yi x I, and that is because so we have squares of weights, so the 1/2 cancels. When you open brackets, so it's this term, or what is left in front of W, and so this is this explains this form of derivative. So it should be equal to 0, and this guy over here, so it should be minus some alpha y yi, and then it should be 0 as well. From here, so we express v as sum of alpha I yi xi. So now I will skip all the intermediate steps. What we do basically, so we take now this result for the optimal solution and put it back into Lagrangian. So instead of these here and b, so you can do it at home. What do we do with this stuff is that yes.
Is it derivative? You go to the next slide. Is it with respect to D or B?
B.
You put B.
Oh, sorry. Oh, yes. Of course, B. But what we do, that's a kind of crucial step here. So we get rid of. So if you look at this formulation, so we have. So W is unknown, so so that's something we want to optimize. B is unknown, so many things are unknown. Plus we have this alpha, so the kind of significance of each sample to this decision. So this problem is very complex. So when we for the specific solution, so for the optimal solution, and the optimality of solution is guaranteed by this, so we find it analytically, and substituting it back to the original Lagrangian, what we do, and then I just write the final step. So we formulate a secondary optimization problem. And the secondary optimization problem, so it looks like this. Where is the final form? So L star is equal to sum of alpha i's minus 1/2 sum for some I, 1 to n, so number of samples, sum of some j, one number of samples. So this is number of samples. And alpha I, y I, alpha j, y j. And here is xi multiplied by xj. So now, so this is the dual problem. So what do we have here? We have here only a single set of unknown parameters. So basically the coefficients alpha. If we solve this problem now with respect to the single parameter, so it solves the above the original formulation. And also what you can do, what you can notice in this formulation, so is this multiplication, the product, which is inner product, dot product between samples. So what we do essentially, if you look at this formula, so it's maybe, well, it's actually not that ugly as it looks from the first glance. So we will compute the dot product between all pairs of samples, and the dot product is this is a measure of similarity. So it's a distance, it's a kind of distance between two samples, and we will optimize this function such so that the final function is minimized by varying the coefficients alpha. So and at the end, what we may expect out of all the samples, most of the alpha coefficients will be 0, and only few of them. And those, I mean, if you just again, so if you slowly trace through previous slides, you will see so that the constraint that we embaked in this problem formulation is that these points should be located on this line. So these alphas will correspond to these support vectors. So the vectors that actually are located at the boundaries of these cloud points. Yes. Now, we have some little time, but I think I will manage to make a couple of comments about it. First of all, so I mean, also even here, so I mean, I used 2D case for the illustration. So the formulation itself, so it doesn't put any limits on x and w. So yes.
Can you repeat where you got the second formula? The second documentation?
This one.
Yes.
Okay. So actually, all happens here on this next slide. So you formulate a model. So this is your original optimization problem. So you want to optimize, you want to maximize this distance between the lines, basically. And you also can formulate the constraints. So in this form. And so Lagrangian method, so it is spelled out here. So you have your function that you want to optimize, and you include the constraints in this in this way. But you don't you do not attempt to solve it immediately because of too many variables that needs to be optimized here. So W vector is unknown, B is unknown, alphas is unknown. But so what you can do, and so you can convert it into into secondary problem, optimization problem, in the at the points where primary problem has optimal decision, problem of solution. Sorry, optimal solution, and optimal solution can be found analytically by taking derivatives with respect to these variables that you vary. So, so the weights and the bias, basically, and so you take the in analytic form. So you take the derivatives, and they become like this. So these two. And now, so you can what you can do from this. So now you focusing only on this optimal case. So you express W, you put and you use that constraint and substitute it here. So if you would just open all the brackets, and maybe still I think it's kind of challenging with this double sums. But I mean, apparently it works. What you do? So you come up with this formulation. So that would be your final problem that you want to optimize, where you have only single set of parameters that you want to find.
I see the transformation that you did for the weights, but I don't see where the summatory of alpha comes from.
So if you would put it in, so what if you would now place W here and the W here, and in and when you open this these brackets, so you will see a term somewhere plus some alpha I y I. I think multiplied by b or so, which basically it is there where you would use this stuff, which makes it 0.
So we substitute them in the end when we.
Yeah. So when you do all the simplification, so you will come up with this model over here. Yes. And now, so you basically can do all these standard ways of numerical methods for finding alphas. So what you do have, you have a huge matrix of dot products. So each with each, and so you basically do this. You apply numerical methods to find this alphas that minimize that L. But again, so what? How do you use it then? So when dual problem is solved, you will select you will have only few samples, so few or just several with alphas greater than 0. And so basically these vectors, I mean the samples, so that's what they what are called support vectors in this stuff. So your model basically so let me see. Maybe not to rush how to do that. Yeah, you remember, so your model, so F, was in the form of Wx plus B. So now you take this finding that W, I mean the optimal values for weights from the above, which is equal to the sum of alpha I yi x I. So that's you calculate the W, and then what is needed is you also need to express B. And B, again, I will skip the intermediate step, so you can find it in the article. Actually, this step is not very complicated. So B is actually yi minus W x xi. Yeah. So you calculate all this, and by this you construct the model, so which will be used for evaluation. For evaluation of whether a sample belongs to a positive class or a negative class. So, but again, so this was a binary classification. So if you want to relax this assumption, so you have two opportunities. You either classify so you can classify one versus all, or one versus one, so multi-class classification. Multi-class classification. So one versus one. So in this case, what does it mean? It means that if you have, say, 10 classes, so you construct this many SVMs. So m minus 1 divided by 2 SVMs. So for basically each distinct pair of classes, and then compute a score. So in each or compute the values of which model gives for each class, and then you basically have a matrix. So for a given sample, so to which class it belongs to, and so some SVMs will agree. So basically, the majority of SVMs will agree on a certain class. Another approach is one versus all. So in this case, you have less SVMs to train. So you take one class and train against all. So you separate one against all the rest. And in this case, so it's faster to train. You know what I will do? So now I will just hang it this problem in the air, but I will return back to this on a class where I will be talking about this hyperdimensional computing. I mean, which is kind of closer to, which is about my research. This I think over here. So you are basically taking so you built a model based on similarity of samples to each other, and so it is here. So we come to the understandings that's to this distinction between linear and nonlinear case. So some samples, in some cases where your data are is linearly separable, like this. So this measure, the distance measure, so between each pair of one class compared to the distance to instances of other class, it will be kind of significant. So distance, so the dot product will be smaller for your own class. However, in nonlinear cases, I mean, there are different like a spiral, or I mean, you remember, so this circle in a circle case. That is not the case, basically. So you cannot draw a line, and this dot product in this case doesn't directly impact the building a separator. And here we come to the need of transforming the data in such a way that dot product after this transformation becomes significant for the decision boundary. And this set of this technique is called kernel method. So you apply transformation, and after transformation, so you can rely on the dot product as a measure of distance to build a separator. And in SVMs, this is done by just applying a certain function here. On this value. So, and there is a theorem that says that, well, you may modify the dot product in different ways. So you apply some kind of non-linear transformation to the dot product, and that kind of simulates a fact of this kernel transformation. But again, so let's come back to this issue later on during one of next classes. That's it for today. Any questions, by the way? Yes.
In the slide where you show the bias, the next one, I think it. Yes, okay. So is it each point has a bias, or why are you taking only i's?
No, bias is common for all.
But why are you taking each sum? Why are you doing y's to by? And not all the y's on the x? Because which I are you going to select?
Maybe I have something. Let me double check. Kind of flashed my my brain the moment. Okay, so see you next time.
I Yeah, yeah.
Hi.
Yes, I have some questions regarding the minimum.
Yeah, sure.